But it doesn't matter because the stupid pen thing is to do with the new version of OneNote, not to do with, yeah. And then the printing has to do with the... So at some point my technology issue should clear up, but it's apparently not imminent. I always say the wrong one. Imminent and eminent. I know which one is which. Imminent means happening in the near vicinity. Eminent means like, ooh. But anyway, important. Blah blah blah. Okay. So yes with sulfide. No with sulfide. Am I right? No with sulfide. Yes with sulfate. No with hydroxide. And yes with carbonate. So we want something that is here and here and here and here. Yes, because we want something that precipitates, something that doesn't precipitate, and does precipitate. And if we look at that, that leaves us with strontium. Cool. Any other questions? Yes? 68 and 69. Okay, which of the following solutes forms a saturated solution when 0.1 moles is in 1 liter of water? Now, what you need to remember for this one is that soluble means you can do greater than 0.1 moles. So we are looking for something that is low solubility because it will be saturated at 0.1 moles. So if we go back here, NH4 plus is always soluble. Na2 is Na is always soluble. And then, so it's neither of these ones, because if we're getting a saturated at 0.1, then it needs to be low solubility. And these guys are soluble. And this one is soluble. How do we feel about that, the fact that they have to be low solubility? Yeah? Okay. Then we need to look at magnesium sulfite and magnesium sulfate. I'm going to guess it's magnesium sulfite because sulfites are low solubility with just about everything, but let's double check. Sulfate, magnesium is soluble, so it's not that one because it would not be saturated at 0.1 molar. It would be unsaturated at 0.1 molar. And then sulfite, yes, magnesium 2 plus would qualify. Is good? Okay. 69, which of the following salts has the highest solubility? All right, so we are looking at silver bromate, bromide, chromate, nitrate. Okay, oh, well that's easier than I thought. What do you see? I don't even need to go look anything up. Why is that? Oops. Because we have nitrate, and nitrate is always soluble. Silver's low solubility with most stuff. We could probably go on our chart and look up silver bromate, bromide, and chromate. Let's go check and see if they're on the KSP table. But I would bet you anything they are. And if they're asking about highest solubility, you can always go with your nitrate salt or your alkali salt or your ammonium salt. But let's go check anyway, just to make sure. We had silver, bromide, bromate, and chromate. Yeah, they're all on our chart here. So if you wanted to confirm low solubility, low solubility, low solubility. Yeah? But you probably don't have to confirm, because if you've got a nitrate there and they're like, oh, one is more soluble than all the others, it's going to be that one. Okay. Any other questions? And we were good with the indicator stuff? Okay, excellent. In that case, we will go to, we were looking at acid-base indicators on page 10, so we're going to be on page 11. Okay, so finding the color of an indicator in various solutions. When you're asked to find the color of an indicator in a solution, you need to find the pH. So this is just a variant on the questions that we had in the previous acid-base 1, where we were like, what is the pH of this weak acid solution? Right? Instead of saying that, we'll say, what is the color of Brom Cresol green in whatever solution it is. Okay, so basically it's saying find the pH and then check the color. And that's the only difference. Okay? Now, what if we have concentration of hydrogen is equal to 1.9 times 10 to the negative 11? What is our pH? How do we calculate that? Negative log, whoops, that's a highlighter. A negative log of concentration of H. (1.9 times 10 to the negative 11), which is 10.72. And at 10.72, what color will Brom Cresol green be? It will be blue, because it turns blue above pH 5.4. Can you guys do the rest of them? Yeah. Excellent. Did you get blue, blue, green? Excellent. Did you get pH of 6.2 for B? Excellent. Now, if you are given the concentration of an acid and you need to find its pH, what's the first thing you should ask yourself if you're finding pH given the concentration of an acid? Yes? If it's strong or if it's weak. So if it is strong, it just completely dissociates, and the concentration of hydrogen is equal to the concentration of the acid. Okay, now if it's a weak acid, what do we need to use? We need to use a rice table. Okay, and hopefully it hasn't been that long since we've done these ones, and we've done a whole bunch of other rice tables in the meantime. No, we haven't. Never mind. What am I talking about? What color is bromcresol green in an 0.025 molar solution of sulfuric acid? H2SO4 is a what kind of acid? Strong. So it dissociates completely. Do both hydrogens come off? No, the first one comes off completely, the second one comes off, but only a very small amount. Okay, recall in a diprotic acid, only the first dissociation makes a significant contribution to the hydrogen ion concentration. So what this would look like is H2SO4 one-way arrow goes to H plus HSO4 minus, which means that the concentration of the hydrogen is 0.025 molar. So pH is the negative log of 0.025, which is 1.6. How are we feeling about my answer? Not great. Why not? Sig figs. How many should I have? 2. So it's going to be 1.60. Okay, and that means that the bromcresol green in this case is yellow. Ugh. Okay. What color is chlorophenol red? In 0.050 molar solution of HCN. HCN is strong or weak? Weak. And when we're talking about 0.05 molar concentration of the acid, is that the equilibrium concentration or the initial concentration? Initial. That is the initial concentration. Remember, we never talk about the equilibrium concentration of the acid. So here's our weak little old lady carrying her bag of rice. She's back. What happened? I don't know. It went crazy. Sorry. I don't know what's happening here. Let's get the mouse. Maybe that'll work better. There she is. All right, and now you guys can do this question. So we're doing what color is chlorophenol red in 0.5 molar? HCN.
you.
Because it's an acid, it's a Ka.
Give me your eraser. Okay, but she wrote water, so actually.
You don't have to write water, you can just have it dissociate, that's okay.
Okay, but for full credits, right?
You know what, if I were writing the AP exam, I would do it this way.
Like with the water.
With the water.
Exactly.
I don't know, what is the Ka value?
Oh wait, I found it. Oh my god. It's there. Right. Right? Yeah, yeah. So then you would do 4.9 times, wait for me, 0.050. And then we got a number like that. I got it. I got it. It's 4.9495. 4.9497 times 10 to the negative 6. That's 266. Oh wait, never mind, you're right. It's the N minus. Wait, and then the HCN. For HCN, you have to do 0.050 minus 4.9 times 6. Right? Right, Dorothy, did you do that? 0.050 minus 4.9 times 6. Because you're minusing it. But why do I need to find it? I don't know. Wait, why are we trying to find pH? Oh, what color?
Uh-huh.
Wait, so we find pH. pH equals the negative log of contribution of H3O. So then the pH is equal.
Did I get it wrong? Did I get it wrong? Oh,
Wait, let me do
I got it right. Amy says I got it right. Times 0.05. Algebra, Tony, algebra.
I got 5.305.
And if that's the case, what color is chlorophenol red? 5.3.
Yellow and red. Orange.
It is orange, yes. Because the chlorophenol red changes from yellow to red, 5.2 to 6.8. And so we're in between, and so we get the orange color. Does that feel familiar enough that it wouldn't be that hard?
Yeah.
Excellent. Okay, not moving, not moving. I've just been lazy and throwing them into the workbook, but yeah, you should. Do you need a Okay, you'll scrounge off of people. Excellent, excellent.
No, it was always that big. This is so familiar. I don't know what my eraser was. I don't think that's why I stole it.
6 fig wouldn't matter here. No, because you want to know what color it is. So as long as you're, doing more than none, you'll be fine. Can I move it now?
I don't know where the body thing went, but
Yeah. Okay. When you are given the concentration of a base, you must also determine if it is strong or if it is weak. So if you remember, all metal hydroxides are strong. Okay? They're all Arrhenius bases. They dissociate completely. So we have all one-way arrows. So you can just find hydroxide using the coefficients from the equation. From there you can calculate H and then pH, or you can go to pH and then pH, POH and then pH. What color is thymolphthalene in 0.0030 molar barium hydroxide? Please carry on and do that one. Well, we're looking for a color again here. So, but yes, it has 2 sig figs if you write it that way. Yes. No. Hang on. Let's go look up what is KW. What is the value of KW? I want to know to lots of sig figs. Whoops, not K2. No, W. There we go. No. KW at 25 degrees Celsius. There we go.
Approximately 1.0.
Hold on. I want to know, I want Wikipedia because it usually gives you things to more decimal places. I don't know. Go with 2 because that's how many it gives. Okay? Yeah. Right. Oh no.
I know. Either way, you can do 14 minus 2.2. That's wait, so the pH is going to be, so it's going to be blue.
Okay, so in both instances, you end up with pH is equal to 11.78. And it is your choice which direction to go, but I wanted to remind you that you can go either direction. You can go from OH to H. Oh, what did I forget there? What did I forget? Charge. Ooh. Okay, and in this case, thymol phthalene will be blue. We will soon learn how to determine the pH of a weak base solution, but we have not yet covered Kb yet, so we will not deal with it on this worksheet. Okay, so there's some questions. Oh no, this is an example. Finding the color of a mixture of indicators.
So you put more than one indicator.
So you put more than one indicator in at a particular pH. What color will the solution be? It's color combining. Okay?
Why are we putting in like 3 different indicators?
Well, shh. Have you guys ever heard of universal indicator?
No.
Okay, universal indicator is an indicator that contains a schwack of other indicators. Okay, so it contains various indicators, and they all change color at different pHs. And so you can have something that is red at pH 1 to 2, orange at pH 3 to 4, yellow at pH 5 to 6, green at pH 7, blue at pH, or like sort of a teal color at pH 6 to 7, it's 8 to 9, 8 to 9, green at pH 8 to 9, and then, teal at 8 to 9, and then blue at 10 to 11, and purple at 12 to 14. Yes? And that's what you get by combining them. So you put a whole bunch of them together and you get this combination. So this is sort of leading up to that. This is just this is playing around with indicators and seeing what you can figure out from them. So at pH 6.4, what color is phenolphthalein? Colorless. At pH 6.4, what color is neutral red? Red. At pH 6.4, methyl red is yellow. Therefore, the solution will be orange.
I got that.
Okay. So that's pretty straightforward. You just, list off the ones you have and then you combine the colors and there you are. This is a lab that we may or may not do. It can be fairly frustrating.
We should definitely do it.
We may or may not do it. You think we shall do it? Okay. Okay. You drip, you get a spot plate. Do you guys know what spot plates are? Okay. And you literally, you got your little spot plates, and into the first one you put some indicator number 1, and you put some HCl. And you see what color does indicator 1 turn? Yes? And it turns red. Yes? Then you put indicator 1 with some NaOH, and what color does the indicator turn? Yellow. So what does that tell you about the acid form of the indicator? That tells you that HIN is red. Yes? And it also tells you that HIN minus is yellow. Yes? So you can go across and you can use the color that it is in HCl and NaOH to tell you the two colors of HIN2, of indicator number 2. What color is HIN2? Yellow. I'm just going to call it yellow because that's too long to write yellow. And then we have IN2 minus, which is blue. And then we have HIN3, which its acid form is red. And IN3 minus is blue. Now, we're going to now we also have weak acids. Okay? And so what we do is we put weak acid 1 with indicator 1. And it turns red. What does that tell you about HA1, its strength, compared to indicator 1? Is it stronger or weaker? It's stronger because it does the same thing as the HCl. So when indicator 1 is faced with an acid that is stronger than it, it will turn red. Yes? So this tells us that HA1 is stronger than indicator 1. How about HA2? Is HA2 stronger or weaker than indicator 1? Is our second acid stronger or weaker than indicator 1? It's weaker, and HA3 is also weaker. Okay, so now we know that HIN1 is stronger than HA2, and we know that HIN1 is stronger than HA3. Yes? Could you go through and make the list for the other ones, your other acids, and then see if you can use that to put them all in order from strongest to weakest? How does HA2 compare to HIN1? Or sorry, HIN. How does HA1, I'm trying to say, compare to HIN2? It is stronger because it turns it yellow, just like HCl turned it yellow. So HA1 is also stronger than the indicator because it did the same thing as a strong acid. How about HA2? Stronger or weaker than indicator 2? Stronger. How about indicator 3, or sorry, acid 3? Yeah, so I'm going to put HIN2 is stronger than HA3. You could write it the other way too if you wanted to. It doesn't matter. I'm just putting them all stronger, stronger, stronger. Okay. Have we done it for our third group yet, or are we still working on that? We're still working on it? Okay. Can you now take those and put together the puzzle? The puzzle is to list all the acids, the HAs, and the indicators, the HINs, in one list from strongest to weakest. You might want a different piece of paper for this. Did I do this wrong? No, I didn't do it wrong. I'm okay. We're okay. Yeah. So if you just wanted to put your HAs in order, who is the strongest of the HAs? The 1s are yellow, the 2s are green, and the 3s are blue. So who's the strongest? What color is the strongest one? Yellow is the strongest one. So yellow is the strongest. And then who's next strongest? Green. And then who's next strongest? blue. Okay, so we know that we've got HA1 is stronger than HA2 is stronger than HA3. Okay. Now, we're going to do the same thing, but we're going to do it for our indicators. I need some more colors here. Let's see, what do we want? We want pink, and we want more colors. We want what? Orange. There we go. Okay. And we want, what other color do we want? Dark blue. Sure. Ooh, dark blue, like it colors really dark. So let's see what we got here. Come on, behave. Good Lord. Ooh, limey green, light green. There we go. Let's try that one. And purple. Purple. Okay. I'm a visual learner, so I like it this way. Okay, so we got orange. Orange is going to be HIN1. Okay. HIN1. HIN2. And HIN3 is going to be our other color green. Let's see if it works. Yeah, it's kind of different. So, who is the strongest out of orange, purple, and green? Orange. And then purple, yes. Yep. And then I really should have chosen a different color, but we're going to go with that green anyway. Better than nothing. Kind of looks like the other green, but that's all right. And so that is HIN1. Purple is HIN2. And green is HIN3. I really should have made it so it didn't go 1, 2, 3, 1, 2, 3, 1, 2, 3. But, you know, what can we do? I should have randomized them. Maybe I'll do that for next time. Anyway, so now we have those. Can we do this with them? Either like this or like this. Do you know what I mean? Who's the strongest? Yeah, HA1 is stronger than HIN1. HA2 is stronger than HIN2, and HA3 is stronger than HIN3. So we can then take yellow is stronger than orange, right? Orange is stronger than green. I don't know. Do I need to do these colors now? I think I can just list them, right? Well, maybe I'll do the colors. What the hell? Purple, blue, and then our other green. Is good? Okay, so basically it comes down to ordering all of your weak acids, ordering all of your weak acid indicators, and then making the two lists go like that. Okay? And I think I have a lot of pages on here about this, but it all just boils down to what we just did. So blah, 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 blah. There. And we didn't need to do any of that. Okay, and then there's some questions here, which is nice. But we're going to move on to 5.2, page 23. Strong bases are most often what kinds of compounds? Metal hydroxides, yes. These fit the Arrhenius definition of a base because what do? They release OH minus in solution. Can you think of an example of an Arrhenius base? NaOH. Any others? LiOH. Okay. How many strong Bronsted-Lowry bases are there? 2. Oh, which ones are they? Yeah, we got our O2 minus and NH2 minus. Okay, excellent. Yep, hardly any, so we won't really bother with them. Okay, weak bases. All weak bases are Bronsted-Lowry bases, which means they are, by definition, proton acceptors. And ammonia is one of the most famous weak bases. Okay, and you can see a hydrogen comes off of the water and it transfers itself over onto the NH3, and we end up with our H, our extra H there. Okay, and then water is left as OH minus. With acids, weak acids, we could cheat and leave the water out of the equilibrium. Can we leave the water out of the equilibrium for the weak bases? Where would the OH come from if there were no water? You have to have the water. Okay, so for weak bases, the water has to be there because otherwise it's like, where is the hydroxide? All weak acids fit not only the Bronsted-Lowry proton donor definition, but they also fit the Arrhenius definition where they simply release hydrogen ions in water. So that's why we can leave out the hydrogen, because we can say, I'm just treating this acid as an Arrhenius acid, so it's just releasing hydrogen. Whereas weak bases, they're not Arrhenius bases. You have to have that water there. Okay. Can't do it, right? Like what? Huh? Interrobang. Do you guys remember that punctuation mark? The interro. Interrobang? No. Ooh, look, punctuation trivia. The question mark exclamation point is known as an interrobang. There you go. Apparently I got excited while I was writing the book as well as right now. I don't know. I'm a grammar geek. So, all in equilibria involving weak bases must involve water or another Bronsted-Lowry acid as a reactant. And since weak bases form an equilibrium, we can, of course, find a KEQ. But because this is a base, we give this KEQ a special name. Can you guess what it is? KB. So let's write the KB expression for ammonia. Check with your neighbor. Easy enough? Excellent. Okay. Finding patterns, organic chemistry. You are not responsible for knowing any organic chemistry, but
I love that.
but what you should know is that you might be thrown a base, a weak base, and like you should just be like, oh, okay, I can deal with this. Yes? Most weak bases are like these ones. These are all some weak bases. And let's find some patterns. What do all of the names of the weak bases, other than ammonia, have in common? They end in INE. And that is pronounced "een." Okay, so we have aniline, hydrazine, ethanolamine, trimethylamine, pyridine, hydroxylamine, dimethylamine. What do a large number of the names of the weak bases have in common? They have dis and tris. What else? What about their endings? Many of them end in amine, amine, amine. Yes? So most of them end in, a lot of them anyway, end in amine. All of them, other than ammonia, end in INE. What do the formulas of all the weak bases have in common? They have nitrogen. They are organic compounds that contain nitrogen. Do you remember the term functional group? Yes? Do you remember any functional groups we have looked at in the past? We had a hydroxyl group. We had a carboxyl group. We had a carboxylate group, carboxylic acid group. Sorry, what? Acetyl. Oh yeah, you got all my biologists here pulling these out of their ears. I've forgotten them all, other than the ones that are relevant to chemistry. Like acetyl, I'm like, I don't know what that is. I know my ketones, I know my aldehydes, I know my alcohols, and I know my amines. Okay, these particular ones are amines. And amines consist of a nitrogen attached to other stuff, very often hydrogens. And if you've done biology, you may have come across this. We have ammonia, which is attached to 3 hydrogens. Hydrogen, hydrogen, hydrogen. What does the R group stand for? The R stands for the rest of the molecule. That's what I say anyway.
Miss Love never told us that.
Yeah, random is good. And it's going to be some hydrocarbon chain of some sort, maybe with some other functional groups on it, who knows. Some hydrocarbon chain. So you might have 3 hydrogens, you might have 2 hydrogens, which gives you an NH2 attached to some stuff. You might have 1 hydrogen and 2 R groups. And you might have a nitrogen with no hydrogens at all. It's just attached to carbon chain, carbon chain, carbon chain. And we call these primary amines, where we have just 1 R group. If we have 2 R groups, we call that a secondary amine. Are you guys familiar with like the little one with a 0, meaning primary? Protein folding, primary, secondary, tertiary.
Oh, yeah.
Yeah, primary, secondary, tertiary, quaternary, yeah. Okay, this is how you abbreviate it with the little 0 at the top, right? They didn't tell you that in biology?
Nope.
Whoa! They made you write out primary,
Yep.
secondary, tertiary. Oh my gosh. Okay, well now you know. You can just like stick that little 0 up at the top and you're good to go. That stands for the whole word.
So is it like the degree?
Kind of. It just, yeah, I think it's kind of like the degree of the amine, but it stands for primary, secondary, tertiary. I don't know. Maybe you're not supposed to learn it. I don't know. Maybe it's a chemist thing. But I don't know. I learned it in biology. Anywho, doesn't matter because I learned it in the context of protein folding.
Protein folding.
Love protein.
Primary structure, secondary folding, tertiary structure.
Alpha helix.
Yeah, beta pleats. Oh yeah. That was my degree.
That was your degree?
Biochem.
Yeah,
Biochem.
we're doing biochem. It's
I love
not
biochem.
It's not it.
Oh, it's the best.
Not it.
Okay. So at any rate, we are looking at amine groups. Oh, we're going to be done in like 1 minute. So let's just call it a day here now that we've been excited about learning how to shorten those words. Okay. And your homework is going to be pages 20 to 22 and studying for your test.
What's this? And your eraser. And your periodic table. Did you have to do cellular reference? Bro, that thing is killing me right now. Like the
NADH.
cellular respiration, like fermentation, glycolysis,
just remember when you stick hydrogens things on it, it gets reduced. When you stick oxygens on it, gets oxidized.
It helps with the enzyme unit where we use the enthalpy thing and the change.
Yeah.
So that test, like, because half of our class is from this class, right?
Yeah.
Or 8 to 5.